Okay, a little bit of business. Let's get started. Let's get started. Let's get started. Okay, a little bit of business first. So if you got my email, I posted a current grade for you. And what does that have? Everything, what did I say? Everything except my math lab and something else? I just did it for another class too, so I'm confused now. A mastery, okay, so that current grade doesn't include the mastery. For those of you who passed it, that's where you get 100, and it'll be worth half of a test grade. And then it also doesn't include the My Math Lab, which is less than half the homework right now. But that gives you an indication of where you're at. And I think is withdraw date Sunday? I think the last day to withdraw is Sunday. Is that right?
Yeah.
Anyway, so I'm not telling anyone to withdraw. So talk to me if you think you're considering that. Talk to me about that. Okay. The other thing is today's recitation. You'll have a quiz as normal, and don't forget a calculator. You're going to need a calculator for at least one of the questions. So bring a calculator to recitation. Yeah, graphing calculator. If you want to use graphing calculator on your laptop, that's fine. You just have to be honest about that, what you're doing, okay? Anything else about business, recitation? Oh, mastery. So those who didn't pass, if you got a 0, that means you didn't pass. It doesn't mean you got 0. It means you didn't pass. So you'll need to go back on Monday, and you'll take it again. Exact same format. You'll get a different set of 10 questions, okay? So the whole point is that you are good at these rules and you have them memorized, and you can crank out the closed form rate of change functions quickly for the basic rules. All right, any questions about anything like that? Recitation, grades, or mastery? Okay, there's one. In the mastery test, you had problems there was problems like this that I said you weren't responsible for. So let's just do one quickly. We're not going to spend a lot of time on this. But what it's called logarithmic differentiation. Okay, so here's an example. When you have a function raised to another function of x, so this has x's in it, and this has x's in it. None of the techniques we've learned so far work. So here's what you do. We use natural log to help us with this. So if y equals sine x to the x squared, then we can take the natural log of both sides. And then there's a property of logs that say if you take the log of something raised to a power, it's the same as moving that power out in front. Now this is not taking the derivative, right? This is just a property of logs where you can take that power and move it out in front. So then this becomes x squared times ln of sine x. So everyone see that I didn't take a derivative there. I was just applying as rule about logs. Okay, so now that we have it like this, we don't have this situation anymore with one function of x raised to another. We can do this now. How can we do ln of y equals x squared times ln of sine x? Now that's a function, right? That's a function that x on. That's not multiplication. How can we?
Is that 1 over y times the rate of y?
Yeah, so we do implicit. Now we got just do implicit differentiation. Go term by term. So here on the right, we'll do 1 over y times y prime. What will we have on the on the left? What will we have on the right? Product rule. So we'll have 2x times ln of sine x plus
x squared 1 over sine
x squared times
1 over sine x
the derivative of that 1 over sine x
times cosine
times cosine x.
times all of that right side by y.
Right, so this is what we're after. We're after the rate of change of y with respect to x. So, and what does y equal? What does y equal?
Oh, sin x to the x.
Yeah, it's what we were given, sin x to the x squared. So I can multiply both sides by this, which would be multiplying both sides by sin x to the x squared. Cosine over sine, what's that?
Oh, cotangent.
Not tangent, cotangent, right? So when do you use it? You use it when you have one function raised to another function of x. One function of x raised to another function of x. You take the natural log of both sides. You apply this property of logs that allows you to bring that exponent to be the coefficient of the log. And then you use implicit, term by term. I think it's pretty straightforward. I don't think we need to do a bunch of examples. Anybody have a question on that?
So cosine x over sin x is
Cotangent. Yep.
Um,
That's just a identity. What's up?
never mind. I was gonna say, couldn't you avoid implicit by doing or taking? Never mind. I'll move on.
Yeah, we really need to get that thing out of the.
Yeah, I mean, after you do
Exponent.
that, could you do e to the ln y and then e to the whatever on the other side? To get rid of the ln and the y. It seems like more work.
I don't know.
Okay.
Other questions? Okay, can I erase it? Okay, so we want to take, we want to look at the falling ladder again. Here's what we did with the falling ladder. So remember we had the and what were our quantities involved? What were the quantities involved with the falling ladder? Yeah.
the distance from the bottom of the ladder to the wall.
Okay, so this distance right here, what is that? What is it? X. X is the distance from the wall to the bottom of the ladder. And what else? From the ground up to the top of the ladder? Y. Okay. And so we found this relationship between X and Y because that ladder's 10 feet tall. And we saw that we could do, I don't know what this is here. So we could do implicit differentiation, and we could get the rate of change of y with respect to x. We found it was negative x over y, and we analyzed some of those values last time. So now we want to kind of take a different look at this, and we want to bring time into it. Okay? Would you agree that x, there is some rate of change of x with respect to time, and there's also a rate of change of y with respect to time? So now that's talking about two different rates at the same time. So you have a rate of change of x as time goes on, and a rate of change of y as time goes by. So this is the first time we've seen this within a given context. We're looking at two rates at the same time. Okay, and so let's say that the bottom of the ladder is moving out at a constant velocity. So its distance would just be v times t, and its derivative would be?
V times t prime plus t times.
No, t is the, v is the constant velocity. It's just a coefficient. And t is our input variable. So what would be the rate of change?
Rate of change of x with respect to t.
Yeah, and what is that?
Dx over
No, it's v, right? It's v. That's what v is. It's how fast the bottom of it's moving, and that's just our coefficient rule. So t is our input variable. Okay, we could also write this as Adonijah said dx dt. Okay, 2, 8, so you could write it both ways. Okay, well, we'll still have the same relationship of x and y. It's just now we're considering those x and y variables as functions of time. So now, when we differentiate implicitly, it's no longer going to be with respect to x, but it's going to be with respect to time. Okay, so what will be involved then, if we're differentiating with respect to time and x is a function of time, what will be involved in finding that rate of change? So we're going to have 2x to the first, right? But now x is a function of time, and we're differentiating with respect to time. So what do we need? Yeah, we need the chain rule, right? So now, if we do it with x and y with respect to time, then every time we do any derivative, we're going to need the chain rule every single time now. Okay? Okay, so we're going to have 2x times, by the chain rule, derivative of x with respect to t. And then same thing, 2y times the derivative of y with respect to t, and then of course the constant 0. So we can rearrange things, and we get this. So this is different than anything we've seen before because this is a rate. It's how fast the bottom of the ladder is moving with respect to time. And this is also a rate. It's how fast the top of the ladder is moving with respect to time. So it's an equation that brings together two rates. So we've never seen that before, right? So, okay, so we call that a related rates equation because it's an equation that relates more than one rate. So where does it come from? What's this? So if you want to get an equation that relates two rates, what's the source of it? Where is it going to come from? How did we get, so basically, how did we get that? Where did it come from? Okay, chain rules involved. Well, we started out with an equation that related the associated quantities, right? Which one was that? Which was the equation that related the associated quantities?
X squared plus y squared.
Right. So if you want a related rates equation, what do you need first? You need an equation that relates those quantities that you want the rates for, you see? So if you want to relate the rate of change of x to the rate of change of y, then what? You need an equation of x and y. And then we use implicit differentiation with respect to t. Anybody have a question? Does that make sense? This is the whole idea. So in the past, teaching this subject, it seems like students are really resistant to this. They kind of just tune out and wait for the punchline. Like, give me the steps. Well, this is the idea. This is the idea. So when you want to get an equation that relates the rates, so you're going to start by getting an equation that relates the quantities. I can't say it any more simpler. Okay. So what did we get for that related rates equation? So I think it was Is this what it was? Okay, so suppose the bottom of the ladder is moving at 2 feet per second, constant. Okay. So how fast is the top of the ladder going down when the bottom of the ladder is 5 feet from the wall?
The rate of
How fast is the top of the ladder moving when the bottom is 5 feet from the wall? You got everything you need. See if you can solve it. Okay, go. See if I can pause it there. Pretty close. We'll just leave it there. So at this moment, how fast is the top of the ladder moving? At this moment when the bottom of the ladder is 5 feet from the wall. So it's just about knowing what all our symbols and quantities mean. If you know what all the symbols and quantities mean, you can, this is piece of cake. So let's see, got some ideas here. Got some, just one thing about this that you concluded.
That I
Yeah, just.
Well, I went back to our dy over dt equals x over y, and because that's where we found when x is 5, then we went in and we could find the value of y by plugging it into the.
Into which one?
Well, because the x squared plus y squared
Oh, that,
equals 100.
okay.
So by using both of those, I found the y value.
You just really just need this, right?
Yeah.
So he's going to start by getting the y value, or how high the ladder is at this moment when x equals 5. Is it the square root of 75?
Yes.
And what is that? 5 radical 3?
8.66.
Is it 5 radical 3?
Yeah, that works.
8.7?
Yeah.
Looks about right. Okay, tell me something else. Lauren.
The rate of change of x with respect to t would not be the 2 feet per second.
Right here, she wants this to be 2. Agree? Yeah. So this is really just being really confident about what the symbols mean. What do they represent in the problem? dx dt, that's exactly right. It's 2 feet per second. Okay? Good. Somebody else? Sharon, did you get something else on this?
Can you just plug it into the dy dt equals the negative x of t divided by the y, divided by y of t times the rate of change of x?
Tell me.
Negative 5 over 5 radical 3, or the 8.7
Okay.
times 2 feet per second.
That's so she wants negative 5 over 5 radical 3 times 2. And do you get negative 2 over radical 3? Let's get an approximation of that.
Negative 1.55.
Negative 1.55. Is that right?
Negative
1.5. What are the units on that? Okay. Why negative? Yeah, because the positive direction of y is what direction is positive y? Positive y. Yeah, y increases going up. So if we're going down, then the rate of change will be negative. How does how fast it's going down compare to how fast it's going to the right? At this moment, it's going slower, about half as fast, right? It's going about half as fast. Okay, questions on this example? Can I erase?
He gave it to us. Above x equals 5. He said it.
Are we good? All right, cool. All right, so let's do an example. The edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? So, are there more than one rate involved? Is there more than one rate involved? And if so, what if there's more than one rate involved? Could you kind of explain what the rates are that are involved in this? DJ? Just one rate or more than one rate? So let's read the first sentence. The edge of a cube increase at a rate of 2 centimeters per second. Is there a rate there? Yes. Second sentence. How fast is the volume changing? Is that a rate? Got 2 rates, right? So what are we? The centerpiece of our solution is going to be. Here's your clue. What kind of problems? There's a related rate. So the centerpiece of the solution will be what kind of thing? What's that?
How one rate relates to the other.
Right, the equation that relates the rates, the equation that's got both rates in it. That's our goal. That's the centerpiece of this whole thing. It's the equation that relates those 2 rates. How fast the edge length is changing and how fast the volume is changing. Okay, so as a tip, this is what we did. Identify the specific rates involved. We did that. So what's the first rate?
The rate of change of the edge.
What's that, Beth? So it's not really velocity, but yeah, so how fast the edge, it is. So how fast the edge length is changing, and what's the other rate?
How fast the volume is changing?
That's right. How fast the edge length is changing, how fast the volume is changing. So we know that our center, like I said, the centerpiece of this solution is going to be that related rates equation, the equation that brings these 2 together. Okay? So, and where did we say that related rates equation is going to come from? How are we going to get that? Where's that going to come from? What's that? The equation that relates the quantities. So, now we want to ask, what are the quantities associated with these rates? This is the easiest part, right? So, we want how fast the edge length is changing. What quantity are we talking about? No, so just the first one. How fast the edge length is changing. What's the associated quantity with that rate of change? Edge length, right? Edge length. How fast the volume is changing. What's the associated quantity? Volume. Okay, now time is also involved. Of course. But the main ones are edge length and volume. So, if the centerpiece is the related rates equation, and where does the related rates equation going to come from? Equation that relates which? V and S. What is that?
Volume equals edge cubed.
He wants volume equals edge cubed. Agree? Okay, so let's just go through the tips. So we want to write a function equation and find how these quantities are related. Volume equals edge cubed. That's it. The volume of a cube. Volume of a cube. What will be the next step then? Our whole goal.
Find the rate of change of volume.
Both sides?
Yeah, both sides.
With respect to what?
Time.
Okay, so it's going to be with respect to time. Okay, not with respect to side length, but with respect to time, so that we get the related rates equation. So what will it be? With respect to time, dv dt, right? With respect to time, we'll get 3s squared ds dt. And this is the unit for that, right? Centimeters cubed per second is the rate of change of volume with respect to time. Okay, think you can finish it? Let's see if you can finish it now. So the question was, how fast is the volume changing when the length of each side is 50? See if you can finish it up. Go. So what we just found there is, if we take the middleman out there, dv dt equals 3s squared ds dt. It's the centerpiece of the solution. Because, why is it the centerpiece? Why is this the whole kind of focal point of this solution to this problem? Adelaide.
Does it say, it says how fast is the volume changing, like dv of dv dt
Okay.
volume over time,
Uh-huh.
which that's the rate of change.
Right. Okay. So it's giving us its dv dt that it's asking for how fast the volume is changing. And we know that the edges are also changing, so we need a related rates equation. Okay, so what will we do? Here. Let's see. Connor. So here's our goal. So if we're confident about the meanings of all these symbols, piece of cake. So what does that symbol mean right there?
That's the rate of change.
Right. What's that?
It's
Length of the side?
and that's the rate of change of the side.
What is it that we want to find out?
dv dt.
dv dt is our unknown. Christina, that's right.
We have to buy 50
What's that?
by the centimeter of the
Times what?
times the rate.
Not quite. So this tells us that the rate of change of volume with respect to time is 3 times the side length squared times the rate of change of side length with respect to time. Megan.
Would be 3 times 50 squared.
3 times 50 squared times 2. Remember this notation? We saw it once before in my math lab. So that vertical bar means evaluate this quantity when that's true. Okay? When that's true. So 3 times 50 squared, so we wrote 3 times 50 squared times 2. Three times 50 squared times 2. Okay, anybody have a question? So, yeah, sure.
So where do you get the 2 for the rate of time? Rate of 2 centimeters.
Yeah.
I meant.
Yeah, so it's just given.
So what, when we pulled it, we got the derivative, right? That's like the rate. I'm lost from how we went from Vs equals S cubed to 3S squared.
From here to here?
Yeah.
Implicit, it's just implicit differentiation. With respect to time now. Instead of, like before we were doing it, in this case it'd be like with respect to S. But now it's with respect to time. So we go one term by one term. And so then everything will have the chain rule. Not just, like before just the Y quantities had the chain rule.
Yeah.
But now everything will have the chain rule because it's this with respect to time and this with respect to time. So what's the rate of change of capital V? Well, it's just 1, but then by the times the chain rule would be times dv dt. And then what's the rate of change of s cubed? 3s squared, but
Times
by the chain rule ds dt. So it's just implicit differentiation, just like we've been doing.
okay.
You see? Other questions? Okay, you guys try this one all on your own. See if you can do it.
Are these related grades questions usually going to involve like scientific formulas, like formulas that are already determined?
So yeah,
You,
So if we don't
there's a
remember
lot of
our-
geometry in
yeah, if
these.
we don't remember our geometry equations.
Yeah. So if you are working through this solution and you say, "Oh, I need to know this," as I'm coming by, yeah, I can tell you what that is. Okay, in terms of some kind of formula or something. But I want you to kind of realize what you need. Okay, I'm not just gonna tell you. Okay.
Oh, you already knew yours. No. I think that's it. Double check. We're pretty sure it's 4 pi r. Sounds right.
Oh, we never took an homework yet. That's homework, I was right.
So volume's going to be
So there's some different elements to this. It's a little slightly more challenging, but you can do it.
Oh, cool. Interesting. I like it.
Any more homework coming in?
We can talk about this in a second.
Yeah.
Anybody need help? Anybody have a question? Feel free to check with the person next to you.
The volume is given.
Okay.
We're trying to find the rate of regions. Or was it that?
You generated that.
Yeah, use your DR, DC, DV, DC.
I'm trying to square the volume plugged into
What's the centerpiece of this problem going to be? Here's my advice. What's the centerpiece going to be? The problem.
We know D equals 13. That's, we know the rate is 15.
Kind of. It's going to be an equation that brings together what?
And I plug in 1,000
That won't be the centerpiece. That'll be important too.
I don't know that.
What will the centerpiece be? Equation that brings together.
2,000. We don't have ours. We can find ours.
Rate of the volume and the rate of the radius. Where is that equation going to come from? That brings those two together.
Because we're looking for dr.
Equation of the associated quantities.
We know volume is just 1,000.
That's your equation that relates to the quantities. From that, you can use this differentiation, you get the related rate equation.
All of that to the 2 thirds. That's all. So that's all. This giant EV we knew. We found R, and then that the last variable, ERDT. No, I already know. No, I'm saying.
What's the goal? Equation of? So the goal is equation of what? Let's see here. Kaiser, what's the goal? An equation that has what in it? What's that? No, that's not the goal. Well, that's we're gonna need that, but that's not the goal. The goal, the centerpiece, the focal point of the whole problem is gonna be Jacob. What do you want to call that? Okay, but so like, what symbols can we use for that?
D of R over DT.
dRdt. Okay, an equation that's dRdt. What kind of problems are these? Is it just one rate of change? So the goal is an equation of? The equation of dRdt and dvdt. So this is how your thinking should begin. If I can get this, I can solve this problem, right? Because it's telling me how fast the volume is changing. It's asking me how fast the radius is changing. Do you see? So if I can get the equation that brings those two together, called the related rates equation, then I can solve this. I can make some headway. Okay, where is this equation going to come from? Marcus.
You have to know what volume is.
Yeah, so it's going to come from another equation. The equation of the associated quantities. The volume that, or the equation that brings together the associated quantities to these rates. Which is what?
4 thirds I R cubed. Rates of volume.
We already did this. What are the associated quantities with these rates?
Radius and volume.
R
Radius, volume, time.
and volume. Okay, and then yes, of course, time. All right, now we want to write a function or equation to bring together R and V. V equals
4 thirds pi r cubed.
4 thirds pi r cubed, and from that we can get Our goal, right? Our goal. How will we get that?
Take the derivative implicitly.
Wow, I can't seem to miss here. It's a fourth. What's the left side going to be when we take the rate of change? Eric? So we're taking the derivative now to get the related rates equation, right? So what will the left side be when I take the derivative?
4 pi.
No, so we're implicitly, so we're going to do it term by term. So we're going to do this term, and then we're going to do this term. So what is the rate of change of v with respect to t?
Sorry, I'm not.
Okay. Josh, what do you think? dv dt. dv dt. That's how you say it. dv dt. Okay? What about the right-hand side? Tyler?
4/3 pi times by 3 r squared. And then dr dt.
Oh, lo and behold, what did we just get? What is this? What is it?
The equation.
The equation that relates the rates. Related rates. It brings together the rate of change of volume with respect to time and the rate of change of radius with respect to time. What's the unknown? We're trying to solve for this one. So to solve for this one, that means we need to be able to get everything else. Somehow we need to be able to get everything else if we're going to be able to solve for this. So how about dv dt?
We have it.
What is it?
15.
15, right? What about the radius?
We don't have it, but we can solve for it.
How are we going to solve for it? Dan, how are we going to get that radius?
You want to do it by itself, right?
No, see, this equation the unknown is this that I circled. So we need to be able to know everything else, all the other values in this, in order to just solve for what I circled, dr dt. So we can't go on solving this for r. This is our unknown, right? So we've got to be able to get that value. I saw Talia first.
Can you go back to the original volume equation
Uh-huh.
with the 1,000 in for volume?
Yeah.
And solve for R?
So is that what you're going to say, Chelsea?
Yeah.
Yep. So when the volume is 1,000, we can get what the corresponding r is that gives us a volume of 1,000 using that equation. What is it?
1,000.
Anybody get that?
I'll cube it up. Who has it?
I did.
DJ?
6.2.
6.2?
Yeah.
So if this is our unknown, that means everything else, we need to get the values of everything else from something else in the problem. So we had the rate of change of volume with respect to time. That was our 15. And then we can get the radius from the volume equation. So now we can solve for dr dt. 15, so 3's go. 15 over 4 pi over 6.2 squared. Anybody got that? Approximation for that? 0.0311. What's the units on that? If it's rated dr dt, it'd be inches per minute. Okay, is the radius increasing rapidly or slowly? So does that make sense? Does that make sense? Why?
15.
Andrew, does that make sense to you? That the radius is increasing really slowly in this context, in this situation? Can you explain why?
Volume of the balloon is very large,
Okay.
and the rate that the helium is entering it is comparatively pretty small.
Okay.
So the radius is going to change slowly.
Okay. Good. So he's saying the balloon is really big right now, 1,000 inches cubed. All right. And compared to that, it's only 15 inches cubed are entering per minute. So for a big balloon with kind of a slow rate of expansion, your radius is going to just be getting very slowly getting larger. Any questions on the process? So again, in these problems, your goal, the centerpiece, is an equation that relates the rates. Where does it come from? It comes from the equation that relates the associated quantities to those rates. So in this case, it was dr dt and dv dt. So therefore, we need to start with an equation of v and r. And from that equation of v and r, we can get the related rates equation. Identify what you're solving for, and you should be able to, from the information in the problem, you should be able to figure out everything else so that you can solve for the rate in question. Any questions? Okay, I owe you some time because I've kept you late several times, so we'll quit here today. The homework for Monday is my math lab. There's eight of these problems. If you can get 5 of them, that's full credit, okay? 5 of them is full credit. More than 5 is extra credit.